we're going to move on to talking about building out the demand model in Vissim, uh, in terms of what type of volume flows are we dealing with, what kind of routing are we dealing with, things like that. So to start, we're going to be looking at the fleet settings. So we're going to be looking at what types of vehicles are in your network, how are we classifying those vehicles, and what kind of mixes of those vehicles are there, right? So talking about cars versus trucks versus buses, what percentages are we dealing with within our network, and then how are we classifying them. So to kind of get some definitions out of the way, the first thing I want to talk about is in Vissim, we have a differentiation between vehicle classes and vehicle types. And this can confuse some people that maybe are newer to Vissim, so I want to get those definitions out. The first thing that we're going to talk about are called vehicle types. These are different groups of vehicles that are grouped together based on physical and performance characteristics. Um, and these groupings can be as broad or as specific as possible, but the characteristics we're talking about are things like the size, right? Length and width, acceleration profile, occupancy distributions, route choice preferences, things like that. So for example, the default VSIM car is 12 to 16 feet long, 6 to 8 feet wide. It has one passenger, and it might be a little small for you, but this is what the acceleration profile looks like, where we have the speed of the vehicle on the horizontal and the acceleration on the vertical. So the default vehicle types we have are cars, trucks, buses, trams, pedestrians, and bicycles. Um, Now, again, these are very broad categories from a default perspective, but it's not uncommon to duplicate or create custom vehicle types such as HOV2 plus, HOV3 plus, connected vehicles, autonomous vehicles. Maybe you're doing something like an airport model, and so you're modeling TNC, Uber, Lyft, rideshare pickup, electric vehicles, um, connected, autonomous. I think I have that on there twice. But you have different types of vehicles that are grouped together based on their physical and performance characteristics. Now, we typically by default differentiate between cars and trucks at a macro scale. But when you get down to certain facility types, like maybe you're looking at bus rapid transit, or maybe you're looking at managed lanes with different tolling algorithms based on socioeconomic status or based on the weight of the vehicle or something like that. So maybe you want to differentiate between, you want to subdivide, for example, your passenger cars into HOV versus single occupant. Or maybe you want to subdivide your HGV, your heavy goods vehicles, from just all commercial heavy good vehicles to those that are over 10,000 pounds versus under 10,000 pounds, because maybe there's a weight restriction on a bridge or an overpass or something like that. So you can always subdivide these default vehicle types up into more specific vehicle types for purposes down the road. Vehicle compositions is just the mix of vehicle types at an entry point into the network. This vehicle composition does not define the fleet mix throughout the entire model, but just at those boundary points where the flows of vehicles are coming in. That's very important to remember. So, for example, um, on your freeway entrance, you might have like a 5% truck mix, right? Um, but the percentage of trucks that take that first off ramp might be different than the overall truck mix. And so those are going to be taken care of through different mechanisms. Vehicle compositions just deal with when you're pumping vehicles into your model, what is the mixture of cars versus trucks versus buses. Vehicle compositions also deal with that entry speed because the boundaries of our network in VSIM are the edge of the world so to speak, from Vissim's perspective. But in real life, those vehicles are coming from somewhere. So there's going to be an entry speed into the network. What is the average speed of the vehicles as they drive into that portion of the network? So that way they're already going the correct speed by the time you are simulating. Again, the default vehicle composition is a 2% truck mix with 0 buses, and the entry speeds are somewhere between 30 and 35 miles per hour. So it's very common to see new vehicle compositions for different facility types. So if you have a vehicle input on the arterials, it might have the default versus a freeway. You might have a custom vehicle composition for freeway input points where they're coming in at higher speeds or maybe higher truck mixes. The last definition I want to get out of the way are vehicle classes. So these look very similar to vehicle types, but the key difference is a vehicle class has nothing to do necessarily with the characteristics of the vehicle. What a vehicle class does is group together different vehicle types for control purposes. So for example, I like to think of these as any sort of signage that you have on the road is always referencing the vehicle class, right? So you have an HOV lane that says HOV, it might say 2+ motorcycles and buses okay, or something like that, right? Those would all be grouped together. You might have motorcycles, HOV 2+, HOV 3+, and buses all grouped into a class that is allowed to use that HOV lane. And then you have a separate class that are all the vehicle types that are not allowed to use that HOV lane. And so you might have a vehicle class that's called non-HOV, right? And they're blocked from that left lane. Or maybe you have hard shoulder running, which allows for buses and other specific types of vehicles. And then you have non-hard shoulder running vehicles or queue jump vehicles or something like that. So that's what vehicle classes are designed to do. They control the vehicles based on the actions that they want to do. So for example, route choice, speed selection, lane availability, control devices, things like that. Evaluation groups, maybe you want to evaluate a subset of vehicle types together. Parking availability, things like that. Those are all vehicle classes. Now, by default, the vehicle classes again look very similar to the vehicle types: car, truck, bus, tram, pedestrian, and bike. But that's just because, within each vehicle type, at the default level, they're very broad strokes. But what most models do is they're going to subdivide those vehicle types up into subtypes or more specific types, in which case you might have different classes that incorporate some of them and not other ones. So common extra classes that you might see again are HOV versus SOV, or a lot of times I see HOV versus non-HOV. Again, TNC if you're doing something like an airport model. You might also have external cars and trucks versus site-generated cars and trucks, right? So you might be doing some sort of TIA in VSIM, or maybe if you're doing a freeway example like this, you have trips that are being made to the off ramps that you are modeling, and then you have other trips that are just pass through trips, right, where they're staying on the freeway the whole time. And so you might choose to evaluate those independently of each other, and so you'd create two separate classes of vehicles: those that are taking one of the exits and those that are staying on the freeway the whole time. And that way you can measure the travel times more specifically. And again, things like CAV, electric vehicles, things like that. So what we're going to do is, on our checklist, we're going to verify that the appropriate vehicle types and classes are set up according to the scope of our project. In this case, it's mostly going to be checking lists. So in the base data menu, we're going to look at what vehicle types we have in the network, what vehicle classes we have in the network. And then in the traffic menu, we're going to see what mixtures of cars and trucks do we have, or what mixtures of cars, trucks, and buses do we have in the network. Um, So, and again, the mixes, these are just at the entry points. When we get to what percentage of vehicle types take a specific ramp or use a particular facility, that's going to be done on the routing side. So we're going to look at that in a section or two from now, where we're going to be looking at specifically how do we get those mixtures to take the exit, right? What proportion of cars and trucks are taking a particular exit or something like that. So we can boil down to specifics by facility. A lot of times you'll have turn count reports, but we're going to look at those at the route level. Again, this is just kind of at the macro scale level on the boundaries of the network. Okay. Once you have a macro level boundary condition set up, we then need to look at our input flow rates. So again, we're not talking about necessarily turn counts at this moment. We're going to talk about those in an upcoming slide. What we're talking about right now are these boundary conditions. So these entry points into the network. What are the inbound flow rates at those locations? And so in this case, we have a 3.5 hour simulation where our seating period, in this case, I've indicated it as 15 minutes, but it's actually half an hour. Uh, we have our seating period, and then we have a vehicle input profile that we're going to be inputting at this location. So if we look at here, at vehicle input number 1, that is the westbound input onto the freeway. So you'll go out into the field, or the modeler will go out into the field, and they'll collect freeway data and count data, and you'll look at that peaking profile, and they'll recreate it in the network. And so we're going to have to go back and make sure that they've recreated that accurately, as well as creating this seeding period that we want to have. So what we're going to do is we're going to go into the base data menu, and we're going to look at various time intervals that were created. In this case, our model has 15-minute time intervals, but they could be hourly, or they could be 10 minutes or 5 minutes or something like that. It's user defined based on what types of time intervals we want to create for our vehicle inputs. Then once we have those time intervals, we can look at the vehicle inputs list, and we can see the volume of every 15-minute interval. Now, what's important to remember is that these volumes are always measured in hourly flow rates. This is the part that I always hone in on when I'm looking at the counts and things like that at these locations. Again, we're talking about the input counts at the boundaries of the network. We're not talking about turn counts at this moment. Just like, for example, you look at this interchange and you look at the total approach volume coming from the east to the west, that's what this should be. But this isn't going to be a 15-minute count. This is going to be an hourly flow rate. So when we see the number 476, that is referencing 476 vehicles per hour. Not 476 vehicles per 15 minutes. We're going to look at these, and we're going to look at the volumes, and we're going to look at the compositions that are associated with them. And again, with the demand configuration, typically this is going to come from some sort of field count report. So if we look at this, we're looking at the mainline inputs, and these are counts for every 15-minute interval. So we have 6 a.m., 6:15, 6:30, and these are giving us counts. These should be converted into volumes, into hourly volumes. Now, I don't know if these screenshots were taken from the incorrect location or something like that, but generally, if we're going to convert from a 15-minute count to an hourly volume, you typically would multiply it by 4. Right? So we'd expect this 505 times 4 to be roughly about 2,000, right? Um, and so I'm not sure if we're just looking at a different vehicle input, or maybe if this is a wrong location or something like that. But this is just an example on how you would verify, okay, what did our traffic counts look like from the field, and how were they inputted into the network? And again, these should be at a specific location. Once you know that your inbound counts are correct, you can now start to look at turn counts, because the turn counts are going to be they're going to weight however much traffic is flowing into that location The routes are going to take a proportion of that and siphon it off to go left or go right or go through. And so from a routing perspective, we're going to be looking more at proportional turns rather than specific counts at this point. So the way a route works in Vissim is there's a pink decision point. And when a vehicle crosses that decision point, they are randomly assigned one of the multiple destinations that is associated with that decision point. So if we look at this particular model that we're using, it has origin destination static routes rather than turn by turn static routes, which is fine. It's just a different way of doing it. Maybe they had like an origin destination travel demand model that they based it off of or something like that. But basically, there's a decision point, for example, on this Eastern inbound vehicle input, and it's going to have a whole bunch of these destinations at every one of the exits. So if we click on that decision point in the list, you can see all of these potential destinations, and each one is assigned a weight. What in Vissim is called a relative flow, but sometimes it's easier to think of it as a weight. And the way the weight is calculated is it takes that movement weight and divides it by all of the weights added together. And so typically what a modeler will do is they will take a count value and divide it by the total approach volume. So for example, this 138 here, this 138 isn't necessarily indicating that 138 vehicles are going to take that movement. It's indicating of all of these weights added together, the proportion of vehicles that pick this movement is going to be equal to 138 divided by this total. And so if you're entering turn counts, that's the most easy way to do that, because say, for example, you have left through right, there's 50 cars turning left, 100 cars going through, and 50 cars turning right. Well, that left turn volume is going to be 50 divided by 200, which would give you a 25% a weight rate kind of thing. So that's kind of how the static routes are assigned. And then when an individual vehicle drives over that decision point, they are assigned a turning movement based on a percentage chance that they would be assigned. So there's a 25% chance that they would turn left in my example, for example. And so that's how it's assigned, is at the individual vehicle level. And so you can have whole platoons turning left at a disproportionate rate, but over the course of the whole simulation, you should see these relative flows or these weights kind of working out over thousands of individual vehicles. So that's how the static routing works in Vissim. So then after, again, we're going to go through and do an example. We're going to look through the model and look at all this stuff in greater detail. But the next thing we're going to look at after we have our routes determined, we're going to look at our turning movement lane change distances. And the lane change distances deal with how early do cars pre-position in their lane, right? So there's going to be a lot of questions about how do we impact lane utilization and things like that. And so if we look at, for example, a freeway, we can control the lane utilization by picking on those exiting lane connectors and increasing or decreasing the lane change distance. Shorter lane change distances mean vehicles are going to wait until the last minute to get over. And so there's going to be a lot more even lane distribution upstream and then a lot of congestion right before the exit. Versus if you have longer lane change distances, vehicles are going to pre-position in the exit lane much more quickly. So you're going to see a disproportionate lane utilization upstream, but hopefully less last minute lane changes and less congestion downstream. Maybe you might have a longer queue in the right lane, but the through movement will be moving a little bit faster. And so that's a calibration tactic the modelers will use and to replicate field conditions, is adjusting this lane change distance. And so that'll be something that we need to check, is our lane change distance, and make sure that it makes sense for the location that we're determining. And this isn't a global parameter, because as vehicles as users of our network use the network more often, they're, especially commuters that use it every day, are going to know when they need to get over to the left and when they need to get over to the right. And so there are going to be some exits that have short lane change distances, and there are going to be some exits that have really long ones where people stack up in the right lane. And so you're going to be, the modelers should be looking at the lane utilization and calibrating accordingly. So let's go take a look at our demand configuration. And we're going to go in and we're going to take a moment and look at the vehicle inputs, the fleet mixes, the turn counts, and then those lane utilizations. So in our checklist, where we left off was at checking special lane characteristics. And so where we're going to pick up is checking vehicle and fleet settings. So we're going to click that one. Any of these that have us checking a list or something like that, we've tried to make it gray just to kind of indicate, hey, you need to be checking the list as opposed to something in the network. So the first thing we're going to be checking is that fleet mix, right? So we're going to check our vehicle fleet settings. So in this case, we're going to go up to our base data menu. And we are going to look at what vehicle types are included in this network. So base data, what types of vehicles have been included? We're going to open up this list. In this case, we just have cars, trucks, and buses. So they haven't subdivided any of the cars, the default cars or default trucks or buses into subunits, right? Typically buses might be subdivided into something like local versus express routes or maybe a bus rapid transit. Trucks, again, might be differentiated by weight or by size or number of trailers. Cars might be differentiated between number of occupants or maybe internal trips versus external trips versus site generated trips, things like that. But it looks like we just kind of have broad strokes, all passenger cars, all pickup truck, or not all pickup trucks, all semi trucks, and all public transit buses. Then we'll take a look at our vehicle classes to see how they're grouped together. And since we didn't have any differentiation really between our vehicle types, our vehicle classes are going to be very similar, right? We only had one set of passenger cars, we only had one set of semi trucks, and we only had one set of buses. So it makes sense that we only have 3 vehicle classes. But again, if the car, for example, had single occupant vehicles versus high occupant vehicles, you might have classes that are HOV versus non-HOV or something like that. Finally, we're going to go up to our traffic menu and we're going to look at our vehicle compositions. And here we have a few different vehicle compositions, and every time I click on one, you can see on the right, it tells us the vehicle type and the entry speed. So in this case, we have the I-70 car, which is only cars at 65 miles per hour. We have I-70 truck, which is just trucks and 65 miles per hour. And then we have State Road 141. We have car and truck. And then we have arterial car and arterial truck. Now, in this particular model, they've taken each vehicle composition and given it exactly one car and exactly one truck. This is very common to do because maybe they have specific counts of cars and trucks at each location, and it's not a uniform distribution, right? So at this location, for example, there might be a 20% truck mix, and here there might be a 5% truck mix and a 2% truck mix and a 10% truck mix. And so if your truck mixes like that are very different based on the location, you'll see this being done where the compositions are broken up into very specific vehicle classes or sorry, vehicle compositions, because what they're going to do is at these locations, they're going to stack 2 different vehicle inputs at the end of this location, one for cars and one for trucks. Now, if you have a pretty homogeneous vehicle comp throughout the whole network, then you might see one composition that has both cars and trucks. But in this case, it's probably pretty different for every location. So they've chosen to instead have two vehicle inputs. Both ways are valid ways of modeling the network. So once we've determined that our vehicle, the big thing you're going to want to check here though are these speeds and making sure that the speeds make sense, right? We have 35-mile-an-hour arterials, we have 45-mile-an-hour frontage roads, and we have 65 miles per hour mainline freeways. Once we're pretty confident that the vehicle fleet settings are making sense for us, next we're going to check our seating volumes. So again, Vissim starts as a cold start simulation, meaning it starts empty. So cars need to trickle in from the boundary conditions. We've indicated the boundaries as red lines. So you can see the cars are trickling in from these red lines, and they need to travel some distance before they make their first decision, right? So it could be, in this case, 3 or 4 miles before they get to their first stop or their first exit. And so that's at least 3 or 4 minutes of travel time to get to this location. So in that case, we need a pretty good seeding period. So let's take a look at, let's just quickly review our simulation parameters. Remember how we have 1,200 or 12,600 seconds. So we have 3.5 hours of simulation. Our evaluation is waiting. So we have a 30-minute warm-up period, meaning that there's 30 minutes, the first 30 minutes of every simulation, we're not collecting any data. So that's our seeding period. Well, now what we're going to want to do is go into our base data menu. And at the very bottom, we have a time intervals list. So we can open up the time intervals list. And there are time intervals for different object types. So we want to look at our vehicle inputs. And what this will tell you is that our vehicle inputs are set up in 15-minute intervals. And we see we have 14 15-minute intervals. So we have our 12 from 1800 seconds all the way up to the end of our simulation. So these are our 3 hours of evaluations. And then we have two 15-minute intervals that represent our seeding period. So now that we know that we have our seed intervals set up, we can open our vehicle inputs list by right-clicking and saying Show List. One thing people always forget about with this time intervals list real quick is they go to time intervals, but they forget to change this drop down, and so it doesn't look right. You have to make sure that you select vehicle inputs from this drop down right here. Okay. Once you see you have all the correct time intervals, now we can go to vehicle inputs, right click and say show list. So if you right click on your vehicle inputs, select show list. This will open up the list, just like in the link list, the list of all vehicle inputs in the network. I'm going to turn off the background images so that those messages go away. In this case, we have 98 different inputs in the network. But if we look, each one of these inputs doesn't necessarily mean that we have 98 input locations. If I scroll around, we have vehicle input number 1, and that's right here. I can see it kind of highlighting. You can kind of see it highlight on your list. You can also right click and say zoom. So if you right click on number 1 and say zoom, it'll show you that we have this input location right here. And if I highlight vehicle input number 1, we can see all the time intervals listed out here. And we can see that these are all having to do with the cars. So they have specific car input rates. If I scroll down though, this says A&M Zone 1. And if I scroll down, you see we have a second A&M Zone 1. And if I zoom to that location, it's at the same spot, right? So we technically have two vehicle inputs at the same location. And the second one has to do with the truck volume. So in this case, there are two vehicle inputs stacked on top of each other, one inputting cars, one inputting trucks. The other way that we could do this is we could have just one vehicle input that has a combined volume between these two. So here, let me filter real quick and say I want to look for A&M zone 1. So here, I just filtered by A&M zone 1. We could, instead of modeling it as two separate vehicle inputs, we could model it as one vehicle input, where we combine these two numbers, we add them together. But then we would need a special vehicle composition that has a specific percentage split between cars and trucks at this location. So doing it this way is just easier because then you don't need a whole list of 50 different vehicle compositions. Instead, you only need 6 vehicle compositions and you can have 2 vehicle inputs at each location. That's totally fine. And that's a very common way of doing it. Okay. To add additional categories of cars, you would need to come back into your vehicle types and create a new vehicle type, and then you can add it to this composition. And once you add anything to this composition, it'll automatically be distributed amongst these vehicles with that percentage. So again, these values are flow rates. They're not counts. So this isn't, we're not expecting to see 6,500 or 6,600 cars drive out at this location within 15 minutes. What we're expecting to see is a flow rate of 6,600 vehicles per hour. So that'll be what, roughly something like a little over 1,500 vehicles should be coming out at this location in this first 15 minutes. And then we should see, again, roughly about 120 or so trucks coming out per 15 minutes at this location as well. Once those trucks are in the network, now that we have our seating volumes, we've checked our vehicle inputs to make sure that these volumes match up with the counts that we saw in the field, again, based on the total link counts, that they're matching up with those in the field. You in our example files, we put in a appendix for counts, for different counts. So you can go in and find this location in that appendix, right? And so you look for this B2 mainline volumes. So you go find that location on I-70. You would validate that the counts that were made during this time interval match up with the time interval in the simulation. Once you have a flow rate, so now you have a link volume assigned, vehicles are going to start pumping into the network. And that's where the next step we're going to look at are our vehicle routes. And what vehicle routes do is, here's our decision point. So a little ways inbound, after the vehicles have been inputted into the network, they're going to drive down the network and they're going to hit this decision point. So if I click on this decision point and kind of zoom out, we can see it has a destination at all of these exit points in the network. So this is an origin destination rather than a turn-by-turn based model. What we could do is have a static route that says X number of vehicles take the exit and Y number of vehicles stay on the main line. And then there'd be another static route that then determines how many people turn left and go through and go right at the next intersection. Here, what we're doing instead is we are modeling a origin destination. So they're making a decision at all the origin points to find their final destination. So in this case, here's a potential route that they're going to take. Here's a potential route that they're going to take. Over here, here's another one where they take the exit. They take the clover leaf and then they make a right turn to take this exit, right? And so the vehicles that are crossing this point are going to make a decision on which destination they're going to take. So what we need to do is we need to go into the vehicle routes list. So I'm going to take my vehicle routes, right click, show list for our static routes. And this will show us a list of all of the static routes in the network, and we can look at their turn values based on the relative flow, so the weights of the different decisions. So here we can find a specific decision point. So this list on the right are all of the decision point, or sorry, the list on the left are all the decision points. And if we select a particular decision point, this list shows all of the potential destinations of that particular decision point. So we can cycle through these and see all of the different destinations that this particular route has that the cars are deciding between. And again, you could do this turn by turn, so you could have a static route for every turning movement, or every approach for every intersection, or you can combine those together or create an origin destination model. So in this case, this particular movement has a weight of 138 divided by the total of all of these. So if I take all of these real quick, let me just pop open an Excel spreadsheet. Here's all the turning movements. If I do equals 138 divided by the sum of all of these guys, all right, hit enter. It looks like we have roughly 2% of the people are going to take this particular path. So that means that for every individual vehicle that crosses this pink bar right here, 2% of them roughly are going to go to this destination. And so that's how Vissim operates, is at an individual vehicle level. This is going to be very different than any deterministic software or intersection level or travel demand model level software. Vissim always operates on individual driver decisions. And so in this case, each individual driver is going to independently decide which one of these destinations to pick from. From a reviewer's perspective, though, what you're going to look for is just the relative flow and making sure that the proportion of this relative flow matches your field counts. And again, this could be match up as a count of vehicles, or it could be some other number that has a similar proportion to those vehicles. Now, earlier, somebody had a question about how do we get specific vehicle mixes at specific facilities, right? So we talked about the entry point having a specific percentage of cars versus trucks, right? How do we get a specific percentage of cars versus trucks taking this exit ramp? Well, if you look, just like with the vehicle inputs that we have, the static routes, if I look at static route number 1, it has these 33 destinations, right? But if I look here, it says all vehicle types is unchecked, and it's specifically only referencing cars. So the cars have a very specific fleet mix, right, or a specific decision model that they are making to make this particular movement. If I scroll down a bit, we can see that I have another decision point that is at the same location that has the same routes that maybe has a different turning decision mix, right? So in this case, what you're going to do, or what the modeler would do, is they would count how many vehicles took the exit ramp or how many vehicles went to this particular destination. And they would say, okay, 6 of them were cars and 138 of them, or sorry, 6 of them were trucks and 138 of them were cars, right? And so in this case, you'd have 2 parallel sets of demand, one for cars and one for trucks. There was another question that says, how do you get the color to turn on when you click certain values like a vehicle route? The first thing is you'll want to make sure that you are selecting, specifically you have the vehicle routes option selected. And then you'll want to make sure that when you open up this list, so you right click, show list, static routes. In the list, you'll see these little arrows at the top, right? If it has a little X, when you select these objects, nothing's going to happen on your network editor. But if you have these little arrows highlighted like this, when you select an object, on the right, it will highlight the pink bars. And so you'll find a decision that you want to highlight, or you can click it in the network. So you can click on it here and it'll highlight it in your list. And then once you have that highlighted, if you want to see the route, you'll have to actually click on one of the destination points of that static route. So for example, I can click on, there's a decision point right here, and then I can look at all of the destinations that are associated with this decision point. But the key here is to make sure that you have your synchronization turned on. Sometimes it's turned off because you don't want it to do that, but you'll want to make sure that it's turned on, and then that way anything you click on the network will show up in your list, and anything you click on the list will show up in your network editor. Okay. Now, depending on how your data was collected and organized in the field, your routing structure would typically match how you collected the data. So, for example, um, on a model like this, on a freeway, it's not uncommon to use something like a travel demand model with origin zones and destination zones, and then you use something like a dynamic assignment, or you use like a vzoom model to run some sort of travel demand model to gather path flows, in which case you're going to replicate those path flows with the static routes like we've done here, where you have origin, destination, static routes. Another way that you might see a different model done is people have gone out to the field and collected specific turn counts at an intersection, in which case you'll see a decision point and you'll just see 3 destinations, one for each movement. And then those movement weights will be based on the turn count. So it just depends on what type of data the modeler had to set up the model, is how they'll decide to set up the static routes accordingly. In this case, if we look at the vehicle inputs, it says A&M Zone 1. Now, for us, what A&M is referring to is an import. So if you see A&M, that means that they imported it from either Vistro or Visum. And Visum is a travel demand model. So they probably imported the demand from a travel demand model, and that created these vehicle inputs, and that's why the static routes are origin destination rather than turn by turn, because they have some sort of origin destination matrix that they based it off of. Okay. Once you've checked your static routes, the next thing we're going to want to check is our lane change configurations. I'm going to close out some of these lists just so we have more room on the screen. And what we're seeing here on the lane change configurations, so I'm going to use this drop down, select lane change configuration. What we're seeing these numbers be are connector lane change distances. So if I zoom in on a particular location, what we can see is we actually have 2 different decisions here. We have a decision to stay on the main line and a decision to take the exit. And we see a value of 6,000. And what that value is referring to is the lane change distance of that connector. So what the lane change distance of a connector is referencing is saying, if you want to take this exit has 3 potential lanes that you can use. And so if you are not already in one of these 3 lanes, so say you're in one of these 2 left lanes over here, within 6,000 feet of this connector is when you're going to start pre-positioning for this exit. So if I take up my measuring tool and I measure back 6,000 feet, find the 6,000 foot mark, that is right there. And so what this is saying is that the vehicles upstream of this point, the 6,000 foot mark, have free lane selection. They can choose whichever lane they want to be in based on which lane is moving fastest or whatever lane they're comfortable with, and it's kind of random as to what the vehicles are choosing to do, mostly based on how fast they're going though. So typically you'll see a more even distribution. Cars will, they'll kind of spread out and kind of have more homogeneous lane utilization. But then after this 6,000 foot mark, a percentage of the vehicles are going to say, I need to take this exit because their static route is saying that. So this lane change distance is saying once they cross the 6,000 foot mark, they're going to start turning on their turn signals and start to make lane changes. They're not going to get into the lane before 6,000 feet. This is when they start making that decision to make a lane change. So for example, if they're in the far right or sorry, the far left lane, they know I need to be in one of the 3 right lanes. So they have 6,000 feet to make 2 different lane changes, one to the next lane over and then one into those. Once they're in one of the 3 right lanes, then they get again move into free lane selection. They'll pick one of the 3 lanes that they can take that would maintain that exit, but based on speed. So they'll pick on whichever one gives them the best travel time, according to the speed they want to go. Similarly, for the through lane, we can see that there's a connector here with a lane change distance of 6,000 feet. So the same thing goes for the through lane, right? So if people are in the right lane, 6,000 feet in advance, they're going to pre-position to make sure that they're avoiding that exit ramp traffic. And again, the lane change distance will determine how aggressively people pre-position. If we take a look at this exit has a lane change distance of 2,640 feet. So if I measure upstream 2,640, the exit lane pocket is only 700 feet long. So what that means is if I go all the way up to that 2,600 foot mark and mark that, so 2,600 feet right about there, what vehicles are going to do is they're going to start in one of these 3 lanes and they're going to cross this point. If they're in the right lane, they're going to stay in the right lane. And if they're in one of the 2 left lanes, they're going to start to get over into the right lane. And then immediately when this lane opens up, they're going to try to get into the exit lane. So if there was a lot of congestion on this ramp, what you would expect to see is a long queue about 2,600 feet long that fills up this whole area and then goes back 2,600 feet. Now, if the queue extends beyond the lane change distance, what will start to happen is cars will start to creep past the queue and try to cut in line in the queue. And the reason for that is because upstream of this 2,600 foot mark, the vehicles are going to have free lane selection. So they could be in the left lane, they could be in the right lane. So let's say that you're driving along in the left lane, and then you hit this point about a half a mile upstream, and you see a sign that says your exit is in half a mile. So now you turn on your blinker and you look over and you realize, oh, there's a long queue there. So you're going to start to get over and you're going to start to try to find a place to get in. And so you're going to cut in. Whereas if the queue was shorter than this distance, you would immediately try to get over and join the back of the queue. So if you have a lot of congestion or if your lane change distance is really short, you're going to have more people come up in this maybe the middle lane and try and get over at the last minute. And so modelers will use this lane change distance to control that behavior, right? Longer distances mean more people stack up in the right lane. Shorter distances mean that people are going to make a lot more last minute lane change decisions. And so this is a little bit harder to validate in terms of you're not necessarily going to always have a queue length on the freeway or a lane change distance measured from the field network. This is going to be going more based on what analysis you have on the congestion of different exits and things like that. In the reviewer's document, there are some guidelines about lane change distances. My personal minimum for a freeway is usually something like at least a quarter mile or so. The thought process there is how are your roadways signed, right? So if you think about it, um, there's going to be green road signs saying your exit's coming up, and they're usually going to be at like half an hour or half a mile or a mile increments. And so that's kind of where how I would base it if I had no other information. If I was modeling it, I'd go to Google Maps or I'd go to Street View and I'd say, okay, where is the signage for this exit? And so you're seeing 2,600 feet, that's about half a mile or so. 4,000 feet, that's a little over 3/4 of a mile, right? Something like that. So and then calibrate it from there based on the congestion levels that the modeler has seen. On arterials, it gets a little bit more tricky. Um, but again, you're calibrating this based on feel and based on lane change distance. So from a reviewer's perspective, you're going to be looking less at these until you might come back to it after you've investigated things like queue results and turn count results and lane utilization results. Later on, you might come back and look at the lane change distances again and see if that's a reason why those results might be looking weird. Okay. So again, up to this point, we've talked about the fleet mixes coming in. We've talked about how are we routing them through the network, and we've talked about how can we control for that lane utilization on different parts of the network. So I'm going to jump back in. The next thing we're going to start talking about is getting into a little bit about another way that you can model in Vissim with origin destination matrices. Now, Vissim does have a travel demand modeling tool called dynamic assignment, where you can create matrices and create path flows. It's more common for this information to come from like a travel demand model, like we see in this file. It was imported rather than created in Vissim, and that's just a time and budget thing, right? So we could create a travel demand model in Vissim and run it, and it works just fine. It's just to find all the paths and to balance out all those path flows, those require more simulations. And micro simulation is a lot more process and time intensive than doing a macros level model in, say, Visum, where you can run an assignment in a couple of minutes. In Visum, it might take a few hours. So more often than not, if you're doing some sort of OD, it's going to be imported. But just so you know, Visum does have it, and you might see it from time to time, where it does have matrices, in which case you're going to go into the traffic menu, look at dynamic assignment, and you're going to review those origin destination matrices. Um, and then on the actual assignment side, the way DTA works is vehicles drive from parking lot to parking lot. So you're going to have parking lots at the entry points of your network, and then you're going to review those parking lots using the parking lot list. So before I get into intersection control, I'm just going to jump into VSIM just to show you. We do have some graphic overlays for these. So if you have check origin destination matrices, you can use this graphic overlay. And what you're going to do is you're going to go up to traffic dynamic assignment. And what you're going to do is you're going to check on what zones are in the network. In this case, this did import with some zones. So we have different zones. And we're going to look at our origin destination matrix. Unfortunately, though, the matrices weren't imported, so we don't have the OD matrix. But you could look at the OD matrices here, and you can see the trip counts from one zone to the next. And then what you'll do is after you've determined that those are correct or those are valid, you'll look at the DTA configuration. which includes parking lots. So you'll show your parking lot list, and you'll see what you would see in the network is a parking lot at these entry points and a parking lot at the exit points, and vehicles will be navigated from parking lot to parking lot, and they'll find their own pathways there. And so you'll review things. Instead of reviewing your static routes, you'll review your path flows, and your paths will have uh, different volumes associated with them. So instead of looking at those yellow static routes, you would instead go up to traffic, dynamic assignment, and you'd look at your path volumes and make sure that your path volumes are fitting correctly. But more often than not, what's going to happen is it's going to be converted to static routes, because we have a button to do that. There's a create static routing from assignment, or it will be imported from another software platform that's already done the assignment. So in this case, there are methods for validating dynamic assignment, but we're not really going to cover them in this course today. If you have any questions on it, or you come across a DTA network that's been submitted to you, you could always reach out to us at PTV, and I'd be more than happy to talk you through it or give you more guidance on it as well.